morning. Right. Good morning, everyone. We're going to continue our conversation about sequential design. So today's agenda is really two topics. Number one, analysis. Number two, implementation, just like what we did for combinational logic. We want to analyze how an implementation works, try to interpret the functional behavior from implementation, and also we're trying to implement the specification behavior into a set of gates and some flip-flops. This is what we saw from yesterday. So there are four flip-flops we care about: D, T, SR, and JK. They have different characteristic behaviors. D supports set and reset. So essentially, this will propagate whatever happens at the input to the output at the positive edge of the clock. The second, T flip-flop can do hold or toggle. So internally, based on the T input, we'll toggle the previous state or hold the previous state. SR flip-flop supports three operations: 0, 0, 0, 1, 1, 0. Those are valid operations. 1, 1 is invalid, and that should never happen at the inputs of the SR flip-flop. And finally, JK repurposes the 1, 1 combination to be the toggle operation, and therefore it supports any kind of input combinations. And in general, the way we build sequential circuit is we put down a few flip-flops and build a combinational circuit controlling these DT, SR, JK inputs. And you can summarize this behavior in a table format. You can also write it out as an equation. So this equation describes the next state, Q plus, in terms of the inputs and the current states. So for D, actually, the next state is the current inputs. For T, the next state depends on the current state and the inputs. And similar things goes for SR and JK. They depend on both the SR, JK inputs and also the previous state. And do you remember how we derive these characteristic equations? From the K-map. Yeah, we put that in a K-map. So the K-map will be a K-map for Q plus in terms of the flip-flop inputs and the current states. Right? And then these are just the minimum expression from each of those K-maps. All right. Now let's actually use this flip-flop to build something, which is like a tiny implementation practice. We can build a D flip-flop from an SR flip-flop, just like what we did with the SR latch and D latch. We can use a single input to control both S and R, but complement that input for R. So if D is 1, we're going to set it, so Q becomes 1. If D is 0, we'll reset it, so Q becomes 0. Right? Indeed, if you look at it from the input-output interface, D and Q, it works exactly like a D flip-flop. And one thing I want you to pay attention to is sometimes the clock is usually denoted by a small triangle. Sometimes we put it on the side. Sometimes we put it at the bottom. But they really mean the same thing. And the clock is often also omitted if the context clearly indicates that we're talking about a flip-flop. Right, so don't worry too much about the representation. As we put down this box and we tell you it's a flip-flop, then you can assume that the clock is right in there. What about a more complicated example? Let's say if I want to build a JK flip-flop from a T flip-flop. So T flip-flop is a sequential component. It's actually also like a tiny little sequential machine. Same goes for JK. So JK is like a small sequential circuit whose behavior is defined by the characteristic equation of the JK flip-flop. So now we're really trying to build a small sequential circuit using a T flip-flop. And this is what we do. Right, we need to add on some additional combinational logic at the flip-flop inputs to make that conversion happen. So this is called the next state logic. It's also called the glue logic, a way to glue together a component with the input-output interface to realize the functionality of a different component. What I have down below is this is the characteristic, the K-map for JK flip-flop. So JK and Q defines Q plus. That's how the next state should work according to the JK inputs. What I have over here is the combinational function that I put at the input of the T flip-flop. So how did I go from here to here? Right, this one comes from the definition of JK. This one is what I need to implement. Right, so the question is, how do I derive that K-map? Well, I can examine each case one by one. So for example, I want to make sure that if JKQ are all zeros, my next state is a 0. That's what I want to ensure from that combinational function. So what do I need to put at the input of the T flip-flop? Well, based on the current state, which is 0, and the next state, which is 0, I want the T flip-flop to receive an input of 0. The T flip has to hold to realize the 0 to 0 transition. And therefore, I put down a value of 0 in that K-map. I just have to do this analysis one by one. For each condition, I do such an analysis. For example, the next one, again, 0, 1. So JK corresponds to the set condition. And next state is a 0. And if you look at the difference between the current state and the next state, so this is the Q axis. This is the value for Q plus. Their relationship can only be realized by holding the T flip-flop. And therefore, that allows me to fill out the second entry in the T input K-map. Right, I'll show you one more example. Next case, I want Q to go from 0 to 1 when my input is 1, 1. Right? I want to toggle it. And therefore, the internal T flip-flop needs to receive the toggle input of 1. And that is represented by the third entry in the T flip-flop input K-map. I do this one by one to gradually fill out that K-map. And then I'll find the minimal expression from the K-map, right, which translates to, I need a surface to write. So this is JQ plus KQ, which is exactly what I implemented at the T flip-flop inputs. That is a combinational function corresponding to this K-map. So this is like a motivational example for the implementation process, and we'll see this in more detail, in more technical detail, and with more complicated examples in 1 second. The idea is to start with, this is my targeted behavior, and I observe the difference between the current state and the next state, and then to figure out what do I need at the flip-flop inputs to activate that transition. And once I fill out the K-map, that K-map gets converted into a combinational function through the regular logic minimization process by finding prime implicants implemented as a sum of products. Right. Yeah. Any questions? Yeah, anything, any ideas? Anything you want to talk about? So this is a tiny implementation exercise. I'll also show you a tiny analysis exercise. So now assume this is the circuit I give you. And I don't know what it does. I want you to recover the behavior of this circuit by describing it in terms of like a K-map or truth table. So what you can do is you have to think about how sequential circuit gets evaluated. At any moment in time, we have a current state. That is the current value at Q. And then there's some new inputs coming in. And then I will evaluate this combinational circuit first to calculate the flip-flop input value. I use that T value to internally update the flip-flop. So run the evaluation happens at 2 separate stages. Stage number 1 is to go through this combinational logic to get the flip-flop inputs. Stage number 2 is based on the flip-flop inputs and also the current state. It will internally update it based on its characteristic table. So combinational circuit, typically, we just evaluate input-output relationship. For sequential circuit, we have to do 2 stages of evaluation. First, through the combinational logic, and then through the internal behavior of the flip-flop. Right. So given this circuit, if I want to analyze its behavior, I better write out this combinational logic as a Boolean equation, right? Which is T equals JQ prime plus KQ. And internally, the flip-flop will work based on its characteristic equation. That's when you give it a particular T input, how we update the Q value to get Q plus. Right. But if you look at the characteristic equation, next state is defined in terms of t and q. Right. But t, the t variable, is really another combinational function. Right. I started looking at the flip-flop. So the flip-flop will work based on the t inputs. But t inputs comes from another combinational function, right, defined on the left. So what you can do is you can substitute the t variable from the characteristic equation with its combinational function. So I'm trying to substitute t with this expression, right, which is shown at the bottom. So t gets substituted by the combinational logic. Now what I get over here is a way to describe q plus, my next state, in terms of j, k, and q. And that's what I want. I want a way to describe the overall behavior of the circuit, which should describe q plus in terms of q, j, and k, which are like primary inputs to the sequential circuit. Right. Does it make sense? Mitchell? I see a bit of visual confusion. Do you have like any specific questions? No. Anyone else? Any questions? So trying to evaluate the sequential circuit, and evaluation happens at two stages. I have to go through the combinational logic and then the internal characteristic behavior to find out the q plus. I'm just trying to combine those two evaluation stages into a single expression so that I can directly describe q plus in terms of the primary inputs and the current state. Right, so let's say if we do the substitution, and then we apply a whole bunch of Boolean transformations, distributivity, elimination. This is what I end up getting. And that's exactly the characteristic equation of a JK flip-flop. So that's what I should get after analyzing the sequential circuit. So this example confirms that, well, when we do the implementation, and then when we analyze the implementation we do get back to the original characteristic equation, which is the intended behavior of this tiny sequential circuit. Right. That's really one way of doing evaluation. In general, we can also analyze the circuit through simulation by plugging in some concrete values on JKQ and to see what happens. Right? But this kind of algebraic method, well, it might be a little bit easier to some people, since you don't have to deal with concrete binary numbers. But if you like, you can also run simulation. What I mean by simulation is, plug in value, let's say 0, 0, 0, and see what I get. So 0, 0, 0 gives you 0 here and 0 here, which makes t a 0. So the current q is a 0, so my q plus will be a 0. And that allows you to fill out the first entry in the K-map. Right? With simulation, we just try every input combination. And then there's essentially 3 bits needed for constructing this K-map, describing the overall behavior, J, K, and Q. And then you try all 8 combinations. You fill out the K-map. And the minimum expression you get over here should also be the characteristic behavior of a JK flip-flop. Right. Remember, with combinational circuit, these are also the 2 ways we can analyze it. We can run simulation, putting down some 0 and 1s at the inputs and see what we get at the output. Or we can try to write it out as a Boolean expression and then simplify it. So both of these ways should give you the same description of next state in terms of primary inputs and current state. So to summarize this sequential evaluation process, the starting point is usually a current state. That is the current state of my circuit, represented by a flip-flop output. And I first need to go through this combinational circuit to get the flip-flop inputs, and then internally, based on the characteristic equation, get my next state. And overall, I get my next state based on the current state and the primary inputs. You can describe it in terms of the connection between these components. First, go through the combinational logic, and then the flip-flop, or in terms of the variable names. We're calculating the t inputs, and then we're calculating the q plus. Yeah, anyone has some questions? All right. So now, OK, with those 2 small examples out of our way, we're getting into we're giving the implementation process a more formal treatment. Right? So formally, how do we implement the next state logic for any given flip-flop? And what we need to implement a circuit, to implement a sequential description, is through the excitation table of a flip-flop. The excitation table is almost like the inverse of a characteristic table. Characteristic table describes how the flip-flop operates according to a flip-flop inputs. Excitation table describes what you need at the flip-flop inputs to realize a particular transition. So for example, if you want your state to move from 0 to 1, and that might be a requirement from the specification, what you need is to put down a 1 at the flip-flop inputs. Right? In fact, for any transition, the D value is equivalent to your expected Q plus. And that makes sense for a D flip-flop. D flip-flop is like a transparent flip-flop. It only saves the D inputs to the flip-flop on the next cycle. For an T flip-flop, the excitation behavior depends on also the current state. So if you want your flip-flop to move from 0 to have a next state of 0, you need to hold it by putting a 0 number at the T inputs. If you want the flip-flop to go from 0 to 1 on the next cycle, you need to toggle it. So T input has to be a 1. 1 to 0, that transition can be realized by toggling the flip-flop. 1 to 1 can be realized by holding it. You have the characteristic table, and we can always derive the excitation table by examining all of the state combination from the current state to a next state, and to see which operation enables us to realize that transition. That's essentially what we did for that earlier implementation example. We look at the next state behavior, and this next state table describes what is the transition needed between Q and Q plus. So Q are these row headers. Q plus is the value that we put in the table. And for any transition, we need to compare them and to see, based on the excitation table, what needs to happen. So I'm going to again go through a few examples. So let's say at this condition, jk equals 0, 0, q equals 1. If you compare q and q plus, q is the row header, which is 1. Q plus is also 1. So I really need my flip-flop to hold the previous value. And therefore, I put down 0 in that combination logic K-map. And assuming that that table is empty and we're trying to fit it out, and we fit it out based on the next state behavior that we're looking to implement together with the excitation table. Second example, for that 0, the state transitions from the current state of 1 to the next state of 0, which can be done by toggling the flip-flop. So the T input needs to be a 1. Right, on the next entry, Q and Q plus, that's a 1 to 0 transition, which can be realized by toggling the flip-flop. So T input is a 1. And finally, 1 to 1, we need to hold the flip-flop. So T input is a 0. Right, we have done that for the bottom row. You can do the same analysis for the top row and to completely fill out that K-map, and then convert this K-map into the combination logic to implement the target sequential circuit. All right, I think now it's time for you to try out an exercise. I'll do the SR, and then I'll ask you to do the JK. So we have done the excitation table for D and T based on their characteristic tables. We can also do that for SR and JK flip-flops. So let's say if I want my SR flip-flop to go from 0 to 0. Right, what are some operations that can allow that to happen? Any ideas? Right, what do I need to put at my S and R inputs to enable the 0 to 0 transition? Yes, Clayton. Yeah, you can probably hold it, or can reset it. Right here, we actually have a choice. We can hold a 0 to 0. We can reset a 0 to 0. Both of them are equally valid. They allow the next state to be a 0 from the current state of 0. So you have a choice. What do you mean by you have a choice? Well, as long as you put the S input to be a 0, then you can realize the transition. You don't have to worry too much about the R input. Right, if S is 0, that allows me to move from 0 of the current state to a 0 on the next state. And that can be very compactly described as 0x. You'll see the reason why we prefer this X in a second. This X essentially allows us to implement a more optimal combination logic. Right? Remember, we're going to use this table to fill out that K-map for the combination logic. And the more don't cares you have, the smaller you can make that combinational circuit. All right, very nice. And from 0 to 1, well, the only valid operation for that would be to set the flip-flop. Right. 0 to 1 can be done by set, so we put down 1, 0 at the SR. 1 to 0 can be done by reset, so we put down 0, 1. 1 to 1, again, we have two choices. You can hold it or you can set it. Both of them will give you a 1 as the next state. So you can set it or hold it. And those two conditions can be compactly represented as x0. All right. And then I'll give you 2 minutes to work out the excitation table for the JK flip-flop to try it out by yourself. Again, based on the characteristic table, to see what are some operations that allow you to make a transition happen, and then try to represent the JK condition in the most compact way, with as many don't cares as possible. Right. The 2-minute timer starts now. Yeah. If anyone has some questions or needs some additional clarification, just let me know, and then I can come over and help you out. Yes. So this table describes the next state, sometimes based on the current state. So if you want your state to go from 0 to 0, the current state in this cycle, and Q plus is the state on the next cycle, you want to apply a particular input to the SR. And I say if you put it as 0, 0 to hold it, indeed, the next state will be a 0. Right? So current state is 0, you put down the new SR input of 0, 0, next state will be a 0. If your current state is 0, you put down, let's say, the reset input 0, 1, the next state again will be 0. So we can say that if the relationship between Q and Q plus is what you're trying to implement, we want to convert that back into some SR values. In that case, either hold and reset will do the job. So as long as I put S to be a 0, I can realize that transition. All right, time is up. So if you have completed this, could you tell me how many don't cares do you have in that table in total? You have 4? Yeah, we have 4 don't cares. And you see, JK is a little bit more powerful than SR because we can also use the 1-1 case if that benefits us. So you should expect a few more don't cares in the JK excitation table. Right. So again, let's examine the case one by one. 0 to 0 can be done by hold or reset. So that's a 0x. 0 to 1 transition can be done by set or toggle, which is represented by 1x. 1 to 0, you can toggle it or you can reset it. So x1. 1 to 1 can be done by hold or set. So x0. All right. I'll see based on our previous implementation exercise. To implement a circuit, we start with some description of the expected next state behavior, and then we try to map it into some flip-flop inputs. And the more don't cares you have, the more likely you're going to have some don't cares in that implementation K-map for the combinational glue logic. So it's more likely that JK gives you a better circuit compared to SR. So what we just accomplished is essentially building this small sequential circuit for JK flip-flop based on the T flip-flop by going through the excitation table. So the question that remains on the table is how do we model sequential designs in general and implement them? Right? How do you convert some kind of a behavioral description into a formal model and subsequently, without any ambiguity, implement it? And to do that, what we need is a finite state machine. This is a very common modeling tool for sequential behaviors. You might have heard it as finite automata in CSE 105. I think Mitchell was talking to me earlier. Have you heard about this word? CSE 30, I see. Right? So in this representation, you can create a node for each kind of state your system can sit in and create a transition between states if there's an input condition that can trigger that transition. So for example, when we have this turnstile, it can take two different kinds of inputs. Let's say, in a very old-fashioned way, you can take a coin, and you can also push the gate. At the beginning, the gate will be locked, and when you put down a coin, it will move to the unlocked state so that you can push the gate. And once you push the gate, it will come back to the locked state. But if you put down one coin after another coin after another coin, it will just remain in the unlocked state and probably return you the additional coins. And at the locked state, if you push it, hopefully nothing will happen, and you will remain in the locked state. And this is an abstract machine that can be in exactly one of a finite number of states at any given time. Essentially, at any time, we are at one of the states. And the input allows us to transition from one state to another. So formally speaking, this is called a state diagram. It's also called state graph, FSM diagram, state transition graphs. And they all mean the same thing, a way to represent the relationship between states and transitions. And the graph has two components, a node representing a state that your system can sit in, and transitions. And these transitions connect states. They are also annotated with some input condition that can trigger that transition. For example, you can describe the T flip-flop by itself as a state machine. You have two states because your state, the Q output, could be 0 or 1. So there are two states that your system can memorize. And when your T input is a 0, it will remain at the current state. If your T input is 1, it will transition to the other state. So Q equals 0, Q equals 1, those are the state outputs from the flip-flop, essentially the information that your system can memorize. You should remember what we learned earlier when we talked about error detection and error correction codes. One of them is called a parity code. A parity code adds one additional parity bit to make sure that this overall message has an even number of ones. If the message already has an even number of ones, we are appending a 0. If the message has an odd number of ones, through an XOR gate, we put down a 1 to make sure that this overall message has an even number of ones. And let's say you have a very long stream of binary data, like millions of bits, and you want to verify whether it satisfies the parity code. What you can do is you can build a very simple sequential machine called a parity checker that takes a 1-bit input and produces a 1-bit output. And this checker will be controlled by a clock. And at every cycle, we can process 1 bit from the input data stream. And if you have a million bit, you'll spend a million cycles to process that stream to eventually tell you whether you have an even or odd number of ones. All right. And this parity counter can be exactly implemented using essentially our T flip-flop. So suppose you want to model that behavior in this kind of two-state behavior. Essentially, all you need to remember is whether you have seen an even or odd number of ones before processing the next bit, and then next bit, and then next bit. At the beginning, you have seen no one, so you start with the even number of ones. And whenever you see a 1, you move to the odd state. Whenever you see a 0, you stay at the odd state, but when you see a 1, you come back to the even state. So essentially, 1 will transition between even and oddness, and 0 will stay at the current state, right? Because it doesn't change the number of ones you have observed. And you see, that's actually the same state diagram as the T flip-flop except that now we are also annotating the state with a number, and that is the output value. So suppose I wanted to produce a 1 when an odd number 1 has occurred. So whenever I'm at the odd state, the output will be a 1 to tell me that so far I have seen an odd number 1s. When I'm at the even state, output will be 0. Right. So really, in terms of a circuit implementation, you just use a single T flip-flop and then connect the state to the output port. Right. So implementation involves, for one thing, you model the behavior in the state diagram. But secondly, we need to do a few more things. Number one is to define the initial state. When you just power up the machine, what is the state that the machine will sit in? And in this case, we're going to sit at the even number of states, right? Even number of ones. And the second important thing is called state encoding. It's a way to convert some abstract state definition, like even and odd number, into some concrete values that can be stored at the flip-flops, which means we're assigning each state with a binary designation that to be stored at the output of some flip-flops. In this case, I have only 2 states, which can be represented by a single state element. And therefore, let's say I just call this the 0 state. I'll call this the 1 state. So whenever my flip-flop output is a 0, it will indicate that I'm at this state. If my flip-flop output is a 1, I'll be on the right state for odd number of 1s. All right, and that's actually the full implementation. You have this input stream coming through the export. And if it's a 1, it will toggle the state. If it's a 0, it will hold the state. And your output is essentially the same as your state encoding. When you're at state represented by q equals 1, the output is 1. State represented by q equals 0 has an output of 0. So the output comes directly from the output of the state output of the T flip-flop. All right. And this is a lot more meaningful than just implementing those flip-flops. This is actually something that we can make use of, right? To process some binary numbers and then figure out how many ones, whether it's an even number or odd number, after a very long stream of ones. And it's also a lot more scalable than combinational circuit. So think about it, right? If you want to design the same parity checker for 1024 bits as a combinational circuit, you need a 1024-bit input. But with a sequential circuit, you have the luxury of spending more times, spending more cycles, and only process 1 bit within each cycle. So you have a much smaller circuit, but with enough time, you can still process that 1024-bit data stream. And in fact, you don't have any restriction on the number of input bits. Right? It's a lot more scalable than a combinational circuit. Yeah. Any questions? All right. So by the way, so who have seen these kind of things before, like the implementation of sequential circuit? Just want to see. Where did you see that?
I see like the state diagram.
I see. What about the implementation part? And like converting that into some flip-flop description. Has anybody seen that before? I see. All right, just get some idea. All right. And sequential circuit, in general, can be modeled in different ways. Like they correspond to 2 different types of state diagrams. Number 1 is called a Moore machine. Number 2 is called a Mealy machine. All right, they sound like very fancy word. But the only difference is that for this output logic, does it depend on just my state value? Or does it also depend on my current inputs? What we saw earlier from that T flip-flop parity counter, output is the state output. So that is a Moore machine, right? Input has no impact directly on the output behavior. Whereas for a Mealy machine, you're going to build a more complicated combinational logic that takes both the current state and the current inputs. So here are some examples from a circuit perspective, the distinction between Moore and Mealy machine. So if you look at this diagram, and if I ask you whether that's a Mealy or Moore machine, we just check for the output logic and to see if there's any connection between my primary input, which is x, to the output function. In that case, you see the output is the XOR between this flip-flop output and this flip-flop output, essentially the 2 states. So it's a Moore machine. Output z does not depend directly on the circuit inputs. Whereas in this other circuit diagram, output z is a function of the state, the complement of my state variable, and also the primary input X. So that's a milli machine. Right? We simply analyze the connectivity of the output to verify to figure out whether it's a more with no connection to inputs or milli with some connection to inputs. All right. And here's essentially the same picture from a different abstraction level. You can also look at it in terms of the state diagram. For Moore diagram, output will be annotated at the nodes. Right? Essentially put down a line and then put down some number below the state encoding, and that denotes a Moore machine. Whereas for a milli machine, output gets annotated next to the transitions. So transition is triggered by some input number. And if I put an output over there, it will tell me that the output is 0 when my state is 0 and the input is 0. With some additional input information defining the output, it becomes a milli machine. So I would say in general, the difficulty with sequential design is as follows. We're moving across many different abstraction levels. For combinational circuit, we're also doing that a little bit. We moved from a truth table into a circuit implementation. And along the way, we do some conversion, application of Boolean algebra, finding adjacencies through K-map, and that is not a trivial task. For sequential circuit, we're moving through even more levels of abstraction. We start from some behavior description, like a parity counter, and then we first need to model it as this kind of a state diagram. This is a formal model that clearly represents all the input-output behavior without any ambiguity. And subsequently, we need to convert this graph into a circuit implementation through a different layer of translation. So there are many layers of translation happening. And I really hope that, so before start working on this technical problem, try to develop a good understanding of how different levels interact with each other. Like when you do the implementation, what is actually happening? How does this picture relate to something like the circuit picture? Right, they're related, they're actually equivalent, but represented in very different ways. All right, so Moore and milli, these are of course some people. I guess their affiliations. Bell Labs, yeah, AT&T Bell Labs. These people have also worked at Bell Labs for quite a few years. So it also kind of makes sense that Shannon developed this algebra for Boolean, applies Boolean algebra to implement circuits. And at this period, people started to optimize combinational circuits. And a few years later, people started to model and optimize sequential circuits. And I really couldn't find any photo of these two people, which is very sad. All right. So actually, McCluskey, he has also done some work about sequential modeling. So he must be working together with milli and Moore on that kind of projects. All right. And here I have another exercise for you to implement a state diagram, or to draw a state diagram based on some behavior description. Right? That description is saying that design a Moore machine, which means output depends on the state. That outputs a 1 when the number 1 received is a multiple of 3. So 0 mod 3, output becomes a 1. Right? Use as many states as you need. Could you try to draw the state diagram? By just sort of following these kind of patterns. Right? Create a state. Each state has a particular meaning, right? Even and odd for a parity counter. And over there, for a mod 3 counter, you will need a few more states with different meanings. And then add connections between them, annotate the output, and to realize that behavior. Okay, I'll give you 2 minutes to work on it by yourself, and then I want you to discuss with other people in the classroom to share your ideas. Okay, timer starts now. Yeah, again, if anyone needs some clarification on the task, also let me know. Yes, yes, you could have multiple names, and actually you need multiple names. So let's say with one state, one flip-flop, you can represent two states, 0 and 1. If you need 3 states, you need 2 flip-flops, which means every state is represented by 2 bits of information, right? The joint output from the 2 flip-flops. All right, time is up. Could you get into groups of 2, 3 people and then share your ideas and then explain to each other how you designed or architect such an FSM diagram? Michael, could you talk with Delaney? And yeah, you don't have to really complete it. Yeah, just try something and then explain to each other how to think about the problem. What about people on this side? Could you come together and then do some talking? Yeah.
Yeah, mine's not really important.
So what do you think?
I don't really know. So I don't think I can do this.
You could have 3 states.
Because if I do it like this,
Mhm.
I feel like, because it makes it between like how many ones you have.
That's right. Yeah, that is what you need actually.
Oh, that's.
Yeah, just 3 states moving a cycle, right? Mouse is essentially like a cyclic behavior.
Because I was thinking that I had to do it like this. And then,
With 2 states, you can actually prove that it's not possible.
okay.
That's because, think about like how many information contents do you need to differentiate. You really need to differentiate between 3 different modular levels. So 2 bits is like 2 states is definitely not enough information contents to accommodate that that many conditions. Right? 0 mod 3, 1 mod 3, 2 mod 3, they have to be differentiated. So they have to be remembered somehow. You cannot remember 3 different scenarios using 1 bit, like with 2 states. Right? So you do need a bit more states. And Mark, what do you think? Do you have any specific questions or any specific thing that you find difficult? Or is it about the general modeling of the state machine?
I'm not sure. We'll see.
I see.
That's why I don't really
All right.
judge this.
All right. Does anyone want to share with us how they designed this FSM and then explain to us their thought process? Anyone want to come to the front and then talk with the rest of your classmates? All right. Thank you, Eric, for volunteering. Come over here and then maybe explain to us how you designed it. Or I mean, if you want to connect to your iPad, you can also do it. Oh, there you go.
It within 2 states. Previous 2 bits.
Get a microphone for you.
Oh, do I just clip it? I don't have something to clip it on. Okay. So, does that work? So you can't use two states because you have to save too many bits. So like it would have to be like 1, 1, 1, and it's not possible to save just one bit. So you have to use 3 states where you cycle between how many ones you have currently stored. So in this case, it should be 0. So you start at here with 0 ones, and then when you add a 1, you cycle to 0 with 1 1 that you currently have stored, and then you have another 1, you go to the next one with 2 ones, and then you have another one, then you go back to the starting state.
I see. Yeah, very nice. Could you keep it here, and I want to talk a few more words about your design. So we need 3 states because there's 3 different scenarios we need to remember. 0 mouse 3, 1 mouse 3, 2 mouse 3, and these are different states. You have to remember, so you need 3 states. And then Eric also defined an initial state. That's when you start the machine, essentially we've seen nothing. So like 0 mouse 3. Right? And then remember there are 2 additional things we need to design. One of them is called state encoding, a binary way of representing each state. And with 3 states, you need information to represent it. So you really need 2 flip-flops to make the implementation happen. Which means this state in Q equals 0, Q equals 1, those should also be represented by some 2-bit binary numbers. So you can use like any 3 binary designations as you like, 0, 0, 1, 0, 0, 1, right? Doesn't really matter. And every state will be represented by 2 bits. And eventually be implemented with 2.
Mm-hmm.
The second thing is about the output behavior. So by definition, the machine should output a 1 when the number 1 is a multiple of 3. Output is always a 1-bit output. You're using 0, 1, 2. These are more like the numerical meaning of the 3 states, not the actual output. So what do you think we should put that in? State corresponds to a multiple.
The starting state?
Yeah, it's the starting state. So we want this state to produce an output of 1.
Mm-hmm.
We want the other 2 states to produce an output of 0. So you can put down within each state the output of value of 0 under the
Yeah. Okay.
So it's a nice presentation. It also allows me to take a break. Really appreciate that.
It's okay.
Thank you. Right. So again, for this machine, you need 3 states, and output will be 1 when the state corresponds to a multiple of 3 number of many ones. And you have transitions of 1 allows you to go through the 3 states in a cycle. And then whenever you see a 0, it will remain at the current state. Yes? Yeah, it will always output a 1. Because if you see, let's say at the beginning of your input stream, you see you have a bunch of zeros. Then the total number of zeros is indeed a multiple of 3. Like 0 times 3. Like 0 is a multiple of 3. So your machine will output a 1.
But it wouldn't.
So multiple of 3, let's say you define to be any number that can be represented by 3 times n, where n is an integer. So 0, like you have seen none of the ones, also satisfy that condition of being a multiple of 3.
Oh, I get what you're saying.
Yeah. So you have seen no 1, so 0 is a multiple of 3. You have seen 3 ones, 3 is a multiple of 3. So again, here's a recap of our learning objectives. This is what we're trying to achieve in this lecture and also the next lecture. We're going to see how to implement or specify the sequential behavior using state diagram based on the behavior description. And this is a formal ambiguity-free representation. And we're going to see how to implement that, to convert that into a circuit with flip-flops and some combinational circuit. And also going the other way around, starting from a circuit diagram with flip-flops and combinational logic, derive the state diagram. Right? Those are the 3 main things that we'll see in this class. So I'll start with some analysis example. suppose this is a circuit I give you. I want you to recover the state diagram, right? Think about it for 10 seconds how you would approach it. Right? State diagram is essentially a way to describe, from the current state to the next state, right? What is the input condition? What is my output value? And how many states do you have in total? Right. Does anyone have some ideas like how could you reconstruct the state diagram? All right, maybe I should give you more hints. So this circuit diagram has two flip-flops, which means at any moment in time, your current state is represented by 2 bits. So a combination of this value A, this value B, that is your current state. Your current state is denoted by 2 bits coming from the 2 flip-flops. So your current state could be one of those 4 values, 0, 0, 0, 1, 1, 0, 1, 1. Current state means the value stored at the output of the flip-flops. 2 flip-flops, you have 4 states in total. All right. And to do that analysis, instead of going directly to the state diagram, which is a graphical representation, a more convenient way is to start with this tabular representation. To first write out its combinational behavior and also sequential behavior in a table, and subsequently convert the table into a diagram. So what I mean by this table? Well, the table describes the next state in terms of the current state and your input condition. And to figure out the next state, again, you have 2 approaches. Number 1 is to run simulation. So let's say if my current state is 0, 0, 0, I'm going to plug in those values into my circuit. So these are all zeros. These are all zeros. All right. So for the OR gate, you have 2 inputs of 0, so dB. So each of them is a D flip-flop. And A and B are the corresponding flip-flop outputs. We typically call them D, but to differentiate them, we call them A and B. But really, those are the 2 Q outputs coming from the 2 D flip-flops. And these are D inputs. D inputs for A, D inputs for B. So the OR gate produces 0. The XOR gate produces a 1, which means if my current state is 0, 0, which sits at the output of the flip-flop, and my next input is a 0, the next D input will be 1, 0, which means when you're at the next positive edge of the clock, the state will be updated to be 1, 0. And therefore, this is 1, 0. Any questions before we move on? So I'm running some simulation. Again, I think about the evaluation of sequential circuit in 2 stages. Number 1 is through this combinational circuit to get the flip-flop inputs ready. And D flip-flop is like a transparent flip-flop. Therefore, the next state will be exactly the same as the flip-flop inputs. Any questions? All right, I'll try another example. So let's say my state is 0, 1. Right? So state is 0, 1 coming out of the A and B. So bottom end, again, the X is a 0. So X is a 0. This flip-flop will give you a 0. On the left, the complement of B, which is a 0. 0 XOR 0 is a 0. So my next state would be 0, 0. I also do some color coding for the previous example. Only by looking at the flip-flop inputs of these D flip-flops, I know what is my next state. And you can do this one by one for all the combinations. And you should get the complete table. That's one way of doing it. To analyze a circuit through simulation. And in general, you can also analyze a circuit based on their Boolean expression. Right? So I'll also try the second method. So for D flip-flop, the flip-flop outputs, so Q plus equals D. That is the characteristic equation for a D flip-flop, which means whatever you have at the D inputs will be your next state. And in this case, let's say the next state for A, which is A plus, essentially equal to dA. And dA is a combinational function, x XOR B prime. right? I also write out the expression for B. So B plus equals dB, which is equal to A plus X. With this information, you can almost immediately calculate what are all your A pluses based on this condition. So I'm going to draw a truth table, or actually a K-map for A plus. I have a truth table, describes the A plus in terms of the AB, the current state, and also the primary inputs X. 0. So X XOR B prime corresponds to this K-map. X XOR B prime essentially X XOR B. So if X and B have the same value, X and B are both zeros. Here, X and B are both ones. Output is a 1. And that tells you all my next state for A, the first flip-flop, based on the current state and the primary inputs. And you can use that information to immediately fill out this entire row, like half of your next state column in the state table. Right? Instead of doing them in the evaluation one by one, we directly do an evaluation based on the Boolean expression and then convert that into a K-map. And you'll see the table also follows the same K-map order, which allows you to directly map an individual K-map into two separate columns in the state table. Right? Those are the two columns for A plus, when X equals 0, X equals 1. I just got to do the same for the B variable. Right? For the B variable, that is A plus X, which means if you look at the right, you're going to have, OK, I'll use a different color. Just 1 second. Right. So all the blue colors, the green colors correspond to things related to the B or B plus. And B plus will be 1 whenever X equals 1. So this whole column will have the next state for B being whole column, you're going to have a whole column of 1s. And also the bottom 2 rows when A equals 1. So really you have A equals 1 over here, X equals 1 over there. If you look at them, those two separate columns as a whole K-map, that's how I fill out the K-map. Right, this is the implicant X. These 4 1s are the implicant for A. And this is a lot quicker than running simulation. Right, by analyzing the Boolean expression and then directly fill out the corresponding positions for A prime using for A plus using A plus K-map, and then for B plus using the B plus equation and subsequently B plus K-map. So really, state table is a way to put two K-maps side by side and then overlay them on top of each other, and then use the combined information from both K-map to represent a singular state. Also, let's not forget about the output. Output is the XOR between A and B. So whenever A and B differ, output is a 1. All right. To sum it up, we have two methods. Number 1 runs through simulation, right, plugging all these numbers. Method number 2 is to analyze the Boolean expression over here and knowing its relationship with respect to my next state behavior, and then directly fill out the next state column for A, which happens over here, and the next state column for B happens over here, right, based on those Boolean expressions. And the state table is really a K-map for two functions simultaneously. Here's a better picture. Right? And in general, we do this A plus using one set of K-map. We do, let's say, B plus use a different set of K-maps, and that allows us to quickly fill out those 4 columns. Output is always quite straightforward to evaluate, right? Based on the output function, simply, this is a Moore machine, so look at the state condition, you know the output. Yeah. Yes? Say that again? It's not, the Z is based on the state condition, not the initial condition. So you see the connection? Z depends on the 2 state variables. So like the Q output from this flip-flop and the Q output from here. So it's QA XOR QB, or like A XOR B, which means whenever the current state has 0, 1 or 1, 0, output is a 1. And I promise you that through analysis, you can recover the state diagram. Right? What I just showed you is a state table. But state table and state diagram are really equivalent representations. Like conversion between these two is trivial. Every state, by definition, becomes one node in the graph. So you have 4 states, which translates to 4 nodes. And we need to add some additional transitions based on the input condition. So 0, 0 on the input of 0 goes to 1, 0. 0, 0 goes to 0, 1 on the input of 1. Oops. 0, 1 comes back to 0 on 0, goes to 1, 1 on 1. 1, 1 comes back to 0, 1 on the input of 0, stays at 1, 1 on the input of 1. And finally, 1, 0 goes to 1, 1 on the input of 0, goes to 0, 1 on the input of 1. Those are all my transitions. Right? On the transitions, I also specified the corresponding input conditions. And this is a Moore machine, and therefore output will be annotated on the states. So under each state representation, we have an output 0, 0 produces 0, 0, 1, and 1, 0, output is a 1, 1, 1, output is 0. And that is my complete state diagram. Like, although I didn't specify the initial state yet, right? In general, initial state has to be specified separately. So let's say if with additional specification that 0, 0 is the initial state, then I'm going to put down an additional triangle next to 0, 0. Right? But that has to be specified separately. Any questions? Right, again, a better picture than what I drew. Right, so what I just did is we started from the gate level diagram with flip-flops and combinational logic. We fill out the state table, and then we convert the state table to a state diagram. And that is a more behavioral description of the circuit. And that's one of our learning objectives, to analyze the circuit. And this analysis happens for a D flip-flop, which is one of the easier analyses. And now we're going to move on to the implementation. How to convert the FSM diagram into an implementation? Well, we essentially just reverse the process. Given a state diagram, we can first put it down as a table so that we can more easily analyze like the combinational logic. Eventually, this will be translated into a combinational logic. And by putting them in this 2-dimensional space, following the K-map shape, it's easier for us to derive the combinational function. The goal is to convert the circuit into that picture. With 2-bit encoding, I need 2 flip-flops. And I'm trying to build the combinational logic using some gates and also the output logic. And based on the table, the output logic is pretty straightforward. Output logic is 1 when your state is 0, 1 or 1, 0. So you connect A and B through an XOR gate, and that is your output. The next state logic is a little bit more complicated. We need really to build a 2 output function. We need one function for the A flip-flop inputs, DA. We need another function for these flip-flop inputs, DB. Right? Those are like 2 separate functions we need to construct. But really, the function for A plus happens at these columns, the left column under each input value. Right? Those are for A plus. And you have a different set of columns for B plus. And these are 2 separate functions. There's no dependency between these 2 functions, other than like they use the same set of inputs. But really, you need to implement them differently. So what we can do is we can separate out those columns into separate K-maps. Well, some people, at this point, they can just look at this table and directly write out the Boolean expression. But for clarity, you can separate the A plus columns into one K-map, the B plus column into another K-map, and then do logic minimization separately. again. So what do I mean by separation? Well, I mean I look at all these A plus columns. That is my A plus function based on the state and the circuit inputs. And that goes to one of my K-map. All of these B plus columns, they go to a separate K-map. I'm just copying over this column 1001, 0110, 1001, 0110 to this K-map. All the B plus column 0011, 1111, 0011, 1111 to the B plus K-map. And now the question is, how do I implement those next state function in terms of the current state and the primary inputs? And additionally, we know that A plus equals dA, B plus equals dB. And dA and dB are what I need to implement. So I just find the minimum expression from each K-map. Right. Top and bottom wrap around the implicand and this one. Whereas over here, that is X plus A. And Z is the XOR between A and B. And I just have to translate these expressions into some circuits. I have an XOR function over here for A plus. I have an OR function over here for B plus. XOR for the output. It's the exact opposite of the analysis process. For analysis, we go from there to these three K-maps, put them into a single state table, reconstruct the state diagram. For implementation, we start from the state diagram, separate out into different K-maps for dA and dB, and then convert that into a circuit. Yeah, any questions? Right. And the analysis and implementation examples that we solve here are for the D flip-flop, which is the most straightforward case. Because inside the D flip-flop, the next state equals dA. So you don't have to do so much translation between specification and the implementation. For the other flip-flops, there's an additional layer of translation, which is a little bit more complicated. So just finish our example of implementation analysis for two D flip-flops. And now let's move on to the second example of analysis, which is our last example for today. So now I give you a different circuits implemented with two JK flip-flop. And then these are the combination logic. I'm ignoring all the connection because it's a little bit complicated to draw all the lines, but that's the variable name going into the JK inputs of each flip-flop. And there's also an output function. Right, the question is over here, how do we recover the next state behavior? In fact, I would say it becomes a lot more complicated. And the reason is as follows. To evaluate sequential circuit, we first evaluate the combinational function. And then internally, we need to evaluate the flip-flop. For the D flip-flop, the internal evaluation is trivial. It's a transparent flip-flop. But for JK, internally, it will calculate the next state based on JK and the previous state, right, to toggle it or to hold it. So there's another round of evaluation happening within the flip-flop. Right. So how do we do it? We have two choices, simulation and Boolean algebra. Right, with simulation, you can say, well, I plug in the value of, let's say, the first condition, 0, 0, 0. Right, so these are all zeros. My flip-flop inputs are essentially 0, 0, 0, 0, which is a hold condition, which means my next state is 0, 0. Right, do that for 1, do that for 2, do that for all 8 combinations. You can fully recover the state table. Alternatively, we apply Boolean algebra. What do I mean by Boolean algebra? Well, for one thing, these are combinational functions, and they can be represented as an equation, right? Representing the JK inputs based on the current state and the primary inputs. And then if you look at the characteristic equation of the flip-flop, they describe the next state in terms of the flip-flop inputs and also the current state. So again, we're doing some substitution. So J1 is the first flip-flop inputs. but that's also a combinational function of x, q, 0. So if you substitute j1 with x, q, 0 and k1 with x, now you're describing the next state, q1 plus, based on the current state, the primary inputs, and these are also the current state. And that's what we need, a description of the next state in terms of current state and primary inputs. Right, so these are just a summarization of all the equation that is happening in the circuit. We have two AND functions, and the bottom is the characteristic equation. We need to evaluate through both equations to finally figure out the next state behavior. And the output function is always easy. Right? It doesn't have to go through the excitations or characteristic equation of the flip-flop. So you can always just write out the output function based on that combinational logic. Right, so here's what's actually happening when you put the combinational logic and the characteristic equation together. So we substitute all of these JK variables with the corresponding combinational function as shown on the top. So again, things are color-coded, so you can quite easily see that these are the combinational function, and these are the combinational function, getting into the inputs of the flip-flops. And if we do some additional logic simplification, we get to describe the next state in terms of Q0, Q1, which are the current states and the primary inputs. Right? Now that is a function that matches exactly to what we need in the FSM table, a way to describe the next states in terms of current states and primary inputs. So we do some functional plotting to convert those combinational functions into a K-map. For example, I'll draw one K-map for Q1 plus on this side. X Q1 Q0 0 0 0 1 1 1 1 0 0 1. And let's say this is a K-map for Q1 plus. Right, Q1 plus, then I'm looking at the equation for Q1 plus, which has X Q0 Q1. So 1 0. Oh, sorry. Q0 Q1, that's 0 1 in the K-map. And the X equals 1, so I have a 1 over here. And X equals 0, Q1 equals 1. Which are these two ones. And that is my K-map for Q1 plus. You can put that column at this part, the left part of the state table, right, which matches exactly to that K-map. 0, 0, 1, 1, 0, 1, 0, 0 on the two columns. We can do something very similar for the second function. Well, actually, you can also do that directly in place within this K-map. Right, I'm going to illustrate where these three implicants sit in the state table. So X equals 1, Q0 equals 0. That's the top and bottom implicant. X equals 0, Q0 equals 1. It's this implicant. And finally, Q0 equals 1, Q1 equals 0, which translates to these two implicants. Again, after separation, they essentially have a 2x4 K-map, and then these ones are neighbors, these ones are neighbors, these ones are neighbors, and they can be represented by those three implicants. I'll add a bit more color coding. So the purple one are the two minterms on the 0, 1 row. And what about? And then X prime Q0 are the two zeros on the X equals 0 row. Sorry, the two ones. And then finally, I'll use orange. This one corresponds to the top and bottom implicant. If you like, you can do that in place directly within the table. But if you're more comfortable with having this intermediate K-map, feel free to do so. Right, I did that for the Q1 plus. I directly do it in the table for Q0 plus. So it's really up to you, depending on your familiarity or comfortable level when dealing with the FSM table. Right, whether you can conceptually think of it as just two separate K-maps. Yeah, I know this part is very dense, a lot of equations, and Also, like suddenly we're going from these equations to a table, and this table actually corresponds to exactly an FSM diagram, right? 0, states and transitions and edges, input-output labels, and all those kind of stuff. So I know it's going to take some time to get comfortable with this new representation. Yeah, but any questions at the moment? Yes, Michael. This is a Mealy machine, indeed, right? As for a Mealy machine, at the output column, we would again put down the input conditions. For a Moore machine, we only have a single output column. Mealy machine, we also put all the input enumerations over here. And we can also see that from the output equation. The output depends on the x input. Right? In general, this table, you can also scale it to a 4x4 K-map. If you have like 2 states and 2 inputs, you have 4 columns over here, 4 columns over here. Right? If I have like 1 state, 4 input, you probably have 2 rows over here and then 4 columns over here. So you can just think of it as a different way of writing K-maps. Yeah, any other questions? Right. So here's where we are after like 2 lectures on sequential design. We started by designing latch circuits, putting 2 NOR gates, several NAND gates back to back, creating interconnection, creating combinational feedback. And we can derive the characteristic table and the equation for a latch to describe just how it operates. And we then implemented some flip-flop using 2 gated latches. We have the master latch and slave latch, and then they intertwine and interact with each other to activate at only the positive edge or negative edge of the clock. We can again derive the characteristic table and the equation for a flip-flop, and then also the excitation table, which will be used later for implementation purpose. And in terms of designing a sequential machine, we need to model the behavior in FSM diagram, which can also be converted into an equivalent FSM table. And this table, using the excitation table, can be converted to an implementation. We tried that for the T flip-flop, implement JK using a T based on the excitation table of the T flip-flop. And conversely, you can go from implementation to the table through either simulation or by plugging in the combinational next state logic into the characteristic equation. Right. So that's how all the concept we learned so far interact. So that's everything today. We have seen 2 analysis examples, 1 implementation exercise, and tomorrow we're going to see a more complicated implementation example using JK, SR, and T flip-flop, at which point we actually have to make heavy use of excitation tables.